Right, good evening. Today's lecture is on controllability and pole placement. And one of the issues that we can have with pole placement is that if we try and place a set of poles in a control system where there's a pole zero cancellation, in other words, there's an uncontrollable mode in the system, the pole placement algorithm doesn't work. So before we can carry out pole placement, we need to check the controllability of the system. So what we're going to do in this lecture is check the controllability of the system. Then we're going to discover that it's not controllable. We're then going to remove a pole and zero from the system to come up with a controllable system, for which we're then going to design a pole placement controller. So our first thing to look at is to look at the controllability of this, and in order to compute this we need to do a number of things. We need to produce some set of state space equations of this sort of format for this system, and the best format for that, the simplest one, is the companion form. So we'll obtain a set of companion form state space equations for the system, and then we can compute the controllability matrix. The controllability matrix is going to be given by C, CA, CA squared, and CA cubed. And the reason it's a cubic is it's a fourth order system, so therefore there's going to be 4 lines to this matrix, which is CA to the 0, CA to the 1, CA to the 2, CA to the 3. And if the system is uncontrollable, we can show if the determinant of this matrix is equal to 0, then this system is in fact uncontrollable and unobservable. So this is going to be our little calculation, and the first thing we're going to do now is to compute some state space equations, and then we're going to compute this matrix here and then hopefully show the determinant 0. So we can do this routinely in companion form. The first thing we do is fourth order system, so it's going to be 4 states. So we'll start on this side. So we have x1 dot, x2 dot, x3 dot, x4 dot, and we'll have a 4 by 4 matrix here times x1, x2, x3 and x4 plus another matrix with the input in u. We'll have an output matrix y given by x1, x2, x3, x4. So this now I can write the system in companion form. So this is fairly straightforward. We're in 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1. So we fill in the whole top with zeros, put a 1 down there, put a set of 1s, not on the main diagonal, but 1 off, and then these numbers here are these numbers here in reverse order with negative signs. So it's going to be minus 72, minus 126, minus 67, and minus 14. And these numbers here are those numbers there in reverse order. So it's going to be 12, 18, 6, and 0. So this now is our state space representation of our transfer function. So the next thing we have to do now is to compute the controllability matrix, or in this case observability matrix. So we can write down C first. So that's going to be 12, 18, 6, 0. That's the C. Now what we've got to do is multiply the C by the A. So that means we're going to have to multiply this matrix, this vector or array, by this matrix. So we could represent that as 12, 18, 6, 0. And that'll be into a 4 by 4 matrix here. Which is going to be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus 72, minus 126, minus 14, sorry, minus 67 even, minus 67 and minus 14. Now, we just need a bit of space for this, so I'm going to rub this bit out here and generate ourselves a bit of space. And so we're going to work out, first of all, the observability matrix given by C, CA, CA squared, CA cubed. So that's what we're going to have to compute. So let's start off with the C. That's too straightforward. Let's put in 12, 18, 6, 0. So there's our first part of our matrix. We then multiply the 12, 18 and 6, 0 into this matrix. So we get this multiplies into this multiplies into this, that multiplies into that, and that multiplies into that. So it's rows into columns. And this will come out as 0, 12, 18, 6. So this now represents C, this represents CA. So to get CA squared, we could multiply CA by A and it would give us CA squared. So if we change now this one here to 0, 12, 18, 6, this is CA, so CA times A gives us CA squared. This one slightly more bigger numbers here, minus 432, minus 756, minus 390, and minus 66. This now represents CA squared. So if we now remove this part here, and again replace this now with CA squared, which is minus 432, minus 756, minus 390, and minus 66. Multiply this by this, then we'll end up with CA cubed. So these are quite large numbers. 4752, 7884, 3666, and 534. So this now gives us our observability matrix, and what we're looking to show now is that the determinant of this is 0. So this is quite a tricky determinant. It's going to be 12 into that 3 by 3 minus 18 into the 3 by 3, which we get by removing that line and that line, and it's going to be plus minus plus a 6 times a 3 by 3 matrix formed about there with that one as the 3 by 3. So that's going to give us 3 by 3 determinants to compute, and if we add those up, we'll find that the determinant of this is in fact 0. And this now shows that the system has an unobservable pole. Now, routinely in an exam, this would be quite a tricky calculation to do, and this calculation will be quite tricky as well. But given that you might not be in an examination and you might have MATLAB available to you, it's possible to write some little MATLAB code which might help you with this. So let's just briefly look at that as well, shall we? So we could put C, put open square brackets, that's going to be 12, 18, 6, 0. And we could put A equal to, and then this is going to be the A matrix here. So it's going to be, I'm putting a semicolon there for a new line. Then it's going to be we have to have spaces in between these numbers. That would put in our A, C and A. So then it'd be possible then to compute C times A in MATLAB. Or you could compute C times A and C times A times A times A. And this would work out then, C times A would give you the second line, CA squared would give you the third line, CA cubed would give you the fourth line. And then you could formulate that then into a matrix, as we had a minute ago. And once you've got that matrix, let's say that matrix was called some matrix X, you could just work out determinant of X. And that should, with a bit of luck, come out as 0. So that's an alternative little trick that you can play if you happen to have MATLAB handy on any particular time. So what that's shown us is that the system now, because the determinant came out of 0, it's shown us that the system has a pole zero cancellation. Now, we might be able to work out where the pole zero cancellation is, but this is not always straightforward, because it would involve factorising these two polynomials. Again, if we had MATLAB available, I guess we could factorise this just by putting, say, A equals 6, 18, 12, and then simply typing in roots of A, and that would factorise that one. You could do the same thing to factorise this one, so you could work out what the roots were quite quickly. If you hadn't got MATLAB available, say it was an exam question, something like that, it might tell you that there's a pole zero cancellation at, say, s plus 1 equals 0. So in this particular case, there is a pole zero cancellation at s plus 1 equals 0. So what we have to do now is extract a pole at s plus 1 from this expression and from this expression. So it's going to give us 6s squared plus 18s plus 12. And we do a long division now. I've done that a little bit too high up. Just rub that out. We've got 6s squared 18s plus 12, and we divide this by s plus 1. So this is going to go into this 6s. That's going to give us 6s squared plus 6s. Change the signs on the bottom line, add. Give us 12s plus 12, and that's plus 6, or even plus 12. That'll give us 12s plus 12. Such, and then this we could factorise into 6s plus 2. So the top line can be factorised into 6s plus 1 s plus 2. So we've taken that one there, factorised it like this, and then we can have another go now at doing a long division on this one. So get s to the fourth, 14s cubed, 67 squared, 126s plus 72, and divide this one now by s plus 1, so it's going to be 14s squared, or it's going to be just s cubed actually. S cubed, that's going to be s cubed plus s squared, so change the signs and add. So s to the 4 plus s cubed. When you subtract these, we end up with 13s cubed plus 67s squared. S into 13s squared goes plus 13s squared. So 13s squared times that gives us the 13s cubed. And here we have 13s squared. Subtract these two, these disappear. That leaves us with 54s squared. So S into 54s squared goes 54s. So that can bring this one down. 126s. That gives us 54s squared plus 54s. Subtract these, 72s. Bring down the 72, and this goes into this plus 72. This gives us 72s plus 72. So when these completely cancel, you know you've done it correctly. So therefore we could rewrite this as s plus 1 into s cubed plus 13s squared plus 54s plus 72. So what we've done now is to take the original transfer function and we've factorised out of it a pole 0 at s plus 1, and then because these two now cancel out, we can do away with them. So that disappears and that disappears. And that now gives us a new transfer function. So we'll assume now that transfer function is observable and controllable, and we'll go on now to design a pole placement control system for that. And that's going to be in the next mini lecture.